My name is Terry Donovan, and we'll be picking up this spreadsheet that we began last time. We're going to be building the Hardy-Weinberg equilibrium spreadsheet model. Now, just to recall where we left off last time, we simulated a population of individuals down column A, and there were 1,000 individuals in total. We entered allele frequencies for the A gene, and we said that A1 had a frequency of 0.6 and A2 had a frequency of 0.4. And we used those values to simulate a genotype for each and every individual in our population. Then we came over to this portion of our spreadsheet and we counted the number of A1 homozygotes, the number of heterozygotes, and the number of A2 homozygotes. From here, we were able to calculate the allele frequencies of the simulated population. Now, Jed mentioned that what we typically do is then conduct a test to determine if this population is in Hardy-Weinberg equilibrium or not. And to do that, we would compute the expected numbers of individuals based on the calculated P and Q frequencies. So P is the frequency of the A1 allele and Q is the frequency of the A2 allele. Now, in order for us to get an A1 individual, they need to inherit an A1 allele from one parent and an A1 allele from a second parent. And this is really E5 squared, and sometimes you'll see this written as P squared because P represents the frequency of the A1 allele. Now that'll give us a proportion. What we need to do is multiply this by the population size to generate the number of individuals we expect under Hardy-Weinberg. How about the heterozygotes? In order for an individual to be a heterozygote, they need to inherit an A1 from one parent and an A2 from a second parent. But don't forget, heterozygotes can be manifested in two ways. If the A1 comes from the mother here and the father here, in this case, the A2 is coming from the mother and the father. And so there are two ways in which a heterozygote can be created, and so we need to multiply that answer by 2 and then multiply by our population size to get the expected number of heterozygotes. And finally, an A2 individual is created by receiving an A2 allele from one parent and an A2 allele from the second parent, and we multiply that by the population size, and these numbers should sum to be the same, 1,000, or we've made some kind of mistake. So let's take a closer look at these results, and we've actually graphed those for you. If we click on this chart, we can see that the numbers that make up this chart are highlighted. Here we have the genotypes listed across the horizontal axis and their frequency, or the number of individuals, on the vertical axis. There are two series of data here. The observed data is coded in blue, and the expected data is coded in red. And you can see that when I press F9, I generate new genotype frequencies, and these numbers are automatically updated, but no matter what I press, our observed and expected values match pretty closely, don't they? Here they're a perfect match. Even without using any kind of statistical test, we would probably claim that the observed number closely matches our expected values under Hardy-Weinberg equilibrium, so we would conclude that this population was, in fact, in Hardy-Weinberg equilibrium. What happens, though, if these numbers and bars don't align so well? let's assume that the red bar drops and this red bar over here increases. Then suddenly we're in a position where we need to determine if the population is in Hardy-Weinberg equilibrium or not. And traditionally, we answer that question with a yes, it is in Hardy-Weinberg, or no, it's not in Hardy-Weinberg. And so in our spreadsheet in cell M11, we're going to return the word yes or no. Is this population different from what Hardy-Weinberg predicts? No means the population is in Hardy-Weinberg equilibrium, and yes means the population is out of Hardy-Weinberg equilibrium. Now, how do we do that? Well, traditionally, we calculate a test statistic from the data that we have, and our data is the observed and expected data. And this test statistic is called the Pearson chi-square. As Jed mentioned, you've probably been exposed to the Pearson chi-square test statistic at some point in your schooling. It's a pretty straightforward calculation. You take the observed value and you subtract the expected value from it. And then you square that term. And the reason you square it is because we don't care if the observed number is greater than the expected number or less than the expected number. So by squaring the result, then we basically eliminate those differences. We then take the difference that's squared and then divide it by the expected result. And then we move on to the next column and do the same thing. Observed minus expected squared divided by the expected. And then to the third column, observed minus expected squared divided by the expected. So that's what we'll be entering in cell M7. We'll start by typing in an open parenthesis, observed minus expected, and then we'll square it, and then we'll divide by the expected, plus, let's move to the second column, observed minus the expected, squared, divided by the expected, and then plus our last column, observed minus the expected, squared, divided by expected. And that generates a test statistic. And this is called the Pearson chi-square test statistic. Now, what do we do with this thing? Well, what we do is we look at where this value falls on a chi-square distribution. And the chi-square distribution is a theoretical distribution, and we've plotted it out on a separate tab. So if you click on the next tab, you'll begin to see the chi-square test statistic. The chi-square distribution is controlled by one parameter, and this parameter is called its degrees of freedom. So if I enter the number 2, then a chi-square distribution looks like this. If I enter the number 3, our chi-square distribution has a different shape. So as we change our distribution, you can see that the likelihood of different values plotted here on the horizontal axis take on different values. Now, our example is a chi-square distribution with 2 degrees of freedom, and I'll tell you about that when we head back over to the other page. What we do now is we say we're looking at a chi-square distribution with 2 degrees of freedom. So here's what the distribution looks like. And in cell F2, we enter what we observed as a value. So for example, if we observed and calculated a Pearson chi-square test statistic of 4, then what we want to do is find that number 4 on the horizontal axis and then figure out where this number falls relative to these other numbers in this particular distribution. And if you click on cell F3, you'll see that we used a function called chi-square dist RT. What this function is doing is it's telling us if we find the number 4, it's returning the percentile of the curve that falls to the right of that particular number. So if we find the number 4, the result says that 13.5% of the area under this curve is greater than 4, and 1 minus this value falls to the left of 4. Let's try another number. If we find the number 2, we would find the number 2 in the horizontal axis, and here we see that 36% of the area under this curve falls to the right of 2, and then 1 minus 0.36 falls to the left. And the idea here is that some of these chi-square values are more likely than others. For example, for this chi-square distribution, a value of 0, 1, 2, 3, those are all much more likely than values of, say, 7, 8, 9, and 10. And when we're asking, is our observed value from our data, don't forget the data component, our observed value comes from our data, we're asking, is this an unlikely result or is it a likely result? And if it's unlikely, then we would conclude the population is out of Hardy-Weinberg equilibrium. Now, we're left with this question of what's likely. And by convention, we have assumed that values that are in the far upper 5% of this right tail are considered to be very unlikely or unlikely by chance. There's a very deep historical reason why we use the 0.05 cutoff, and it's debated, but we're not going to go into that here. But for now, we'll just assume that we'll stick with that 0.05 cutoff, and we want to know if our observed value is in that upper 5% region or not. So here you can see the number 2 is not in the upper 5% region. What about the number 5? Well, the number 5 is at the 0.08% region. So 8% of the data under this curve fall to the right of number 5. So we would conclude that that's not significantly different than what Hardy-Weinberg predicts. But if we observed a 6, well, now we're at a place where 6 is at that magical number. It falls below the 0.05 cutoff. 4% or almost 5% of the area under this curve are to the right of the number 6, and then the other 95% falls to the left. So that's what we're going to do with this calculated Pearson chi-squared. We're going to find where this chi-square statistic falls on a chi-square distribution with 2 degrees of freedom. Now, the degrees of freedom, you must specify. You have to tell Excel which chi-square distribution you're talking about. And the way to calculate that is the number of columns minus 1. So we have 3 columns of data, and subtract 1 from that is 2. And you multiply that result by the number of rows minus 1. And there's 2 rows of data here, subtract 1. And so we're left with 2 degrees of freedom. Now, the chi-square test statistic can be calculated using that function we used on the other sheet. This is called chi-square distribution rate. Returns the right-tailed probability of the chi-square distribution. So we're interested in finding our observed test statistic from a chi-square distribution with 2 degrees of freedom. And we see that this particular result is very, very low. In fact, it's falling way over here toward this portion. And so therefore, we would conclude that this population is not different from the Hardy-Weinberg prediction. We'll use an if function here to invoke that 5% rule. We'll find if, and we'll ask if this number, the chi-square test statistic, this is the percentile, is less than or equal to 0.05, then if it is, it's in the far right-hand portion of the chi-square distribution, and so we would say yes, it's different than what Hardy-Weinberg predicts. Otherwise, we'd say no, it's not different from what Hardy-Weinberg predicts. So this question here is the population out of Hardy-Weinberg? And the answer here is no. And we would expect that, right? Based on what we see in our graphic. Now, in this particular cell, I wanted to show you a different way of calculating that, and that's just with the chi-square test function. This function has two arguments where you specify the actual observed range of your data, K5 to M5, and the expected range, K6 to M6, and you press OK, and you can see that these two match perfectly. Now, just to drive this point home, we're going to try to simulate a population where the population is way out of Hardy-Weinberg equilibrium. And you can copy this formula and store it someplace else on your spreadsheet, but I'm going to overwrite my values here, and I'm going to set up a population that consists strictly of A1, A2 heterozygotes. And if I click that through all individuals, we see that our population now consists of 1,000 individuals, no homozygotes. And if we calculate the allele frequencies for that population, as we'd expect, the frequency of the A1 allele is 0.5 and the frequency of the A2 allele is 0.5. When we calculate the expected values, what do we expect these numbers to be if the population were in Hardy-Weinberg equilibrium? We see very different results between observed and expected, and as a result, our chi-square test statistic is enormous. And when we look at where this value falls on a chi-square distribution with 2 degrees of freedom, we see that there's hardly anything to the right of it. So we're talking about this distribution, and we're finding the number 1,000 way the heck over here, and we find that all of the distribution is to the left. That means we're in that very far right corner, and we would say that this population is out of Hardy-Weinberg equilibrium. Here's what this looks like graphically. Here's our observed values, and here's what is expected if the population was in Hardy-Weinberg equilibrium.